Okay, welcome. We can start with the first talk of this session that is from Eloisa Menegoni from the Observatoire de Paris.
Good morning, everybody. So today, what I'm going to show you how we can constrain the scale-dependent bias from galaxy clustering, and so here there is the outline of my talk. So I know that the audience is very heterogeneous, so I will present you some. I will present you a briefly introduction about the cosmological model and the problem that is related to the dark energy problem in cosmology. Then I will show you how we can use the galaxy power spectrum to infer some information from on cosmological parameters, and then I will show you some prediction that we can achieve on the cosmological parameters by using a bias, a scale-dependent bias to infer some information on the cosmological parameters using a Euclid-like survey, and then I will give you my results as a conclusion. So it's very well known that the cosmological model, our universe can be described by a very big explosion. So in the first, that is the Big Bang, and then after this explosion, the universe starts to expand and as an adiabatic expansion. And then after the temperature goes down, we have that the photons are no longer trapped in the primordial plasma, and they are free to travel, and we see these radiation as well described by a black body radiation. But what is important for me in this talk is to see how the dark matter and clusterize in this primordial epoch, and what is the evolution of the dark matter during the expansion of the universe. And also to see which is the component, the component of the dark energy which can induce the formation of the structures that we see today. We know that the universe is very well described by Friedman equation, in which you have that the expansion rate, the Hubble constant, depends on the content of the universe. So, in particular, on the energy density of that is inside the universe. So we have a matter component and a dark energy component. The matter component is formed by a part that is the ordinary matter, that and another part that is the dark matter, in which that we still don't know what is, and is let's say it's about the 75% of the total matter that we have in the universe. And then we introduce this dark energy component. That is the let's say it's related to the energy of the vacuum energy that is composed the universe, and is the only parameter that we can introduce to explain the accelerated expansion of the universe. And then what we observe from our recent results is that the universe is flat, so the curvature is more or less equal to 0. So the big problem of in cosmology, in astrophysics, is to understand what is this kind of dark energy. Because we know that the data and the observation still, let's say that is in very well agreement with the standard cosmological model, which say that this dark energy is described by a factor that is called lambda. That is related to the vacuum energy, but we have still some problem that we can't give an answer. So this is the fundamental important fundamentally important to understand which kind of answer we can give to this dark energy component. And to give some answer to understand what is this dark energy, we have some experiments. In these last years, we have the Planck satellite, but what is important for me now is to show you how we can improve the errors on the cosmological parameters by using the Euclid survey. That will be a survey that will be launched in the 2020. And Euclid will observe all the galaxy. I mean the structure in a redshift between 0 and let's say 2 or 3, more or less. And by using this kind of observation, we can try to give some answer about the the component of the dark matter, of the dark energy, so to the component of the universe, and to understand how the structure that we observe today were originated, and also their evolution. So we have this very good model. I mean, we have this very good experiment like Euclid, and what we want to know is how we can extract some information from the observation on the large surveys to estimate the cosmological parameters. So to understand and to give an answer to the evolution, I mean, of the universe. So what we observe are the fluctuation in the galaxy distribution and not in the mass. So we have to try to find a map, I mean, a relation between the spatial fluctuation in the galaxy distribution and with the mass. This mapping is commonly referred as the galaxy bias. So we have this relation that I mean, it's like a parameterization of our ignorance about the physics of the galaxy formation evolution. So it is important to understand which kind of relation we can introduce to describe this bias. So the bias between the galaxy power spectrum and the matter power spectrum is not only a nuisance parameter. So it's not we can refer to this parameter as only another, I mean, cosmological parameters, but it's very important to understand which kind of relation we can introduce to describe the evolution of the structures. So, I mean, in literature, we use for bias a relation that is like linear, like a constant. But in this work, what I did is to introduce a galaxy bias relation that is scale dependent. So it depends on the scale and on the redshift in which we are observing. And I introduced a power law model and a model that is based on a polynomial model. Yes. And as I said before, I use for the specification of the experiment to do the analysis Euclid-like survey in order to see which kind of constraints we can achieve when we have this kind of survey. And here is the model that we adopt. So here we have the power spectrum, the observed power spectrum for the galaxy, and depends, as I said before, on the redshift and on the scale. And we have different parameters. For example, here, for example, there is the bias relation. And we have the power spectrum observed today, so our redshift zeta equal 0. We have also power spectrum that is like a shot noise that we have to take in account, that it depends on the discreteness of the survey. And to do the analysis, what we did is to construct a Fisher matrix. So the Fisher matrix that we construct is by deriving the power spectrum over the cosmological parameters. For theta E and theta J, we indicate the cosmological parameters. And we had to take in account also the effective volume of the survey. So it depends on the experiment that we take in account. And with this very simple model, what we did is to see which kind of errors we can achieve on all the cosmological parameters. Because the standard, in the literature, we use a bias relation in which we have that this part, B1 and K, to the n is like 0, you know. So the standard relation is the bias equal to a constant, okay. So in this kind of work, we use two different relations. The first one is the power law model, in which we have that we have a dependence to the power of n, and the other is like a polynomial combination in which we have that is based on this paper produced by Cole et al., in which we have that the bias relation is depends on these two Q and A parameters. And obviously, if we took Q and A equal to 0, we achieve the relation, the bias relation that we find in literature. So, as I said before, the Fisher matrix analysis that we have is to have to construct this matrix that depends on the derivative of the cosmological parameters that we take in account. And the error that we can achieve on the cosmological parameters is given by the root square of the inverse of the Fisher matrix components. So, and as I showed you before, what we did is to do these kind of derivatives for the power law model. We have that we had to introduce also to the two derivatives on the Fisher matrix that we construct before. That these are two components that are added to the standard derivatives that we have for the cosmological parameters. And for the Cole model, we have an extra parameter because also we have to add to B0 also Q and A. Okay, so we introduce this kind of derivatives in the Fisher matrix. And as I said before, we use as a specification the specification that comes from a survey that is Euclid-like. So here we have for every beams, every redshift, we have the density for the galaxy, And for the fiducial model, we took this kind of values for the standard cosmological parameters. For example, the Hubble constant, the dark matter component, and so on. For W0, W1, we want to stress the importance of the dark energy component. So we want to see which kind of error we can achieve on the dark energy component by using these two bias galaxy relations. So here there is the results. So the first one, I mean, in this figure we have the likelihood control plot at 1 sigma for B0 and B1 for the first model, in which we have only the power law model. And let's say in blue we have the power law model, which we choose to took as n equal to 2, and in red we have the power law n equal to 1, so a linear relation. And you see that for the errors on the bias for the first model, we have that, let's say that at different redshift, the error bars on the bias B0 and B1 increase with the redshift. And respect to the standard model, we have that the error is larger than, let's say, of a factor of 2. And and in the case of the power law that is equal to 2, we have that the error bars on B0 and B1 are larger than the respect to the previous case. And also we can see also in the plot, because the likelihood are larger for the case in which n is equal to 2. So the constraints are tighter in the case in which n is equal to 1. And so we can see what happens when we use this kind of relation to the cosmological parameters. Also, the cosmological parameters, I mean, the errors are larger. For most of them, I mean, only for, not for most of them, but only for the GRO index, and also for the amplitude of the fluctuation, the spatial fluctuation, and so, and for the other cosmological parameters, like the dark matter component, the baryonic matter component, we achieved more or less the same error bars, and we see that that in this case for the growth rate, the growth rate index and the amplitude of the spatial fluctuation, we have that. The errors are anti-correlated. So if we permit a variation on this index gamma, we can have, let's say, tighter constraints on the sigma 8. Then we perform another analysis in which we say that okay, we have this relation for the bias, and we are observing different beams of the density of a galaxy, or the matter, let's say, at different beams. But we know that the bias can depend also on the redshift. So to perform an analysis in a more realistic case, what we did is to perform, let's say, to do a fit based on a catalog by the H alpha emitting galaxy, in which we can took some reference parameter for the B0 and B1 at a different value of the redshift. So instead to took for B0, for example, B0 equal to 1, as the previous case. We did this kind of fit based on this catalog to understand which kind of reference parameter we can have for the different value of the redshift, okay, and also for B1. And we performed this analysis for different value of n. I mean, and where n is the power of the first relation, in which we have that the bias depends on a power law, and what we did is to do this kind of fit that it was did by this PhD student that he works in Roma 3 with Professor Enzo Branchini, and she gives me the results. I mean, this kind of value. And with this kind of values, I perform another analysis based on the Fisher matrix approach that I showed you before. So, and what we have is that, for example, for the Cole model, that is the second relation that I show you. For the first case, in which we have the non-realistic case, we have that the constraints on Q and A are, let's say, are a little bit larger respect to the control plot and the errors that we can achieve for the model in the more realistic case. And and also, diciamo, sì. And also for we perform another analysis by using for the power law model, as I said before. And for example, for the error on the bit 0, we achieve, let's say, more or less the same results that we achieved in the previous section. I show you before that is like here is like 0.033. Yeah, thanks. And also here with the realistic case, the error on the by B0 for the fifth relation is not larger, is not very large respect to the previous analysis. And so, as I showed you before, also in this case. Also in this case, the errors on the bias parameter are increasing with the redshift, as you see. And also we have, let's say, larger. We have larger errors if we take, let's say, n equal to 2 respect to n2 equal to 1. So just to conclude. What we can say is that for a scale-dependent bias relation, we don't have an increment. We don't have an increase on the error of the cosmological parameters, and so we just find that. For sigma 8 and for the GROW index, we have an we have that the uncertainties is larger than a factor up to 2, depends on the model that we took in account. And what we see is that also that we find that on the for the error bars on the bit 0, we can let's say we can say that we can achieve an let's say an error of, let's say that the error doesn't increase over than 1 or 5%. So thanks.
Thank you very much. There are any questions?
Hi. Just a quick question in two parts. So at the first, in one of the first slides, you showed the W parameters for the dark energy equal to -1.
Yes.
Yeah. Then after, yeah, exactly. After the, yeah, before, exactly there.
Okay. Okay.
And then you said you set these two parameters W0 and W1 equal to minus 0,95. Yeah.
Yes, because
Can you elaborate a bit about that? I do not understand.
No, because for dark energy you use to take a value that is equal to -1, but there are different models in which you have that W is equal to W0, that is equal to -1, plus W1, let's say another value of the for W that is that depends in a linear way with A, that is the scale factor that describes the evolution of the universe. So it's just because let's say that the equation state parameter equals to -1. It's in agreement with the cosmological data, but there are several problems, so that it still doesn't find, let's say, an answer. And so people introduce different relations for the described dark energy. So, for example, this W that depends on a linear way on A, or let's say we can introduce also a scalar field that describes the evolution of dark energy. So it was just say, okay, we have that this value for dark energy equal to -1, but we have also another, let's say, relation because we don't know if it's the right answer. Okay.
The second part of my question was
okay.
When you set the value with the linear dependence W0 equal minus 0,95 and W1 equals something else. Did these values affect your analysis, and
no.
what did you find at the end? I mean, about dark energy.
No, because I mean, what we found is that I don't know if you see here, it's like I think no, okay, here there are not the sigma errors, but the fact is that this kind of relation doesn't have a very impact on the cosmological parameters, apart from the growth of the growth index that describes how the structures are, let's say, are formed, are clusterized, and their evolution, and on sigma 8 that describe the spatial fluctuation. So in the other parameters, they don't have a very big impact. So on the H, on the baryonic component, on the dark matter component, the error bars are not very, I mean, are similar to the reference model, let's say. So the only two parameters that are, let's say, that change more or less, but not too much, are these kind of two parameters, gamma and the sigma 8. So
a last curiosity, just about the scale factor K, how it's really defined. I mean, I did not.
I mean, this analysis we put it equal to, let's say, equal to 1, because otherwise we had different the problem. Let's say we had problem of when the cosmology, I mean the relation starts to be non-linear, let's say. So to do this analysis, we put K equal to 1. So yes, it was just no, K1, yes, K1 is equal to 1. No, K, sorry. Yeah. So.
Other questions?
At some point you mentioned the shot noise. I don't know what that is. Could you please explain it?
This one depends. I mean, on the Euclid. I mean, on the survey that you use to observe the galaxy. So it's very, let's say, server dependent. So because I mean, when you observe the galaxy distribution, you don't observe the only, I mean, only the signal, let's say. You observe also other stuff, so you have to take into account also this one.
Other questions?
Okay, just a curiosity. All these forecasts you made were tailored on Euclid-like mission, right?
Yes.
So if you have barely a detection at 2 sigma level, it means that, for example, DES, dark energy surveys, that is producing results right now, so we could in principle look for it, doesn't stand a chance to see it. I mean, have you looked into?
No, I didn't do it for other surveys. So it was just for Euclid survey. So actually, I don't know if we can achieve some improvement from the other survey. But in principle, I don't know.
Okay. Thanks, Eloisa, again. And, okay, the next speaker is Lichen Liang from the University of Zurich, and okay.
Okay, thanks the organizers for organizing this conference and giving me the chance to give a talk today. Okay, so my name is Lichen Liang. So I'm a PhD student, based at the Institute of Computational Science at the University of Zurich. But the material that I'm going to talk about today is based essentially from the work that I did in master when I was in University of Victoria, Canada. So most of the credits should be given to Victoria. So the thing is that we study galaxy distribution. So we know that the distribution of galaxies is not even in the universe, but on large scales we see aggregates of galaxies. So galaxy groups is basically the smallest aggregates of galaxies in the universe. So its counterpart is galaxy clusters. It's a smaller version of galaxy cluster. The Y group is particularly interesting compared to cluster, is that because these systems are really have relatively lower potential well. So numerous studies has revealed that galaxy groups is the ideal system for studying the feedback processes from the galaxies. So one interesting part of galaxy groups is that it is accessible to X-ray observations. We know that it is permeated by the hot diffuse X-ray luminous gas, which is very interesting. The properties of this hot halo gas is subject to the feedback process related to galaxy formation and evolution. For example, the feedback from supernova and the supermassive black holes in the center of the galaxies. Now, there are some standard problems in galaxy groups. The first one is the notorious overcooling problem that 2 decades ago, or 3 decades ago, people discovered that the cooling time of that hot halo gas in the center of the groups and cluster is way much shorter than the halo formation time. So there's supposed to be like continuous star formation happening in the central galaxies, but we didn't observe that. So what's the mechanism that quench this star formation, quench the cooling? The second one is the missing baryon problem. So compared to the cosmic mean, the baryonic mass fraction of galaxy groups is way much lower than the cosmic mean value. The third one is the core entropy. So in astronomy, we just use this proxy of entropy. So it's not the real physical entropy, but for the observers, it's more easy to define the entropy as in this way. But this proxy has a monotonic increasing relationship with the real entropy, so it's not a big deal. So the problem is that we see that on the large scale of the groups and cluster, the entropy fulfills a power law with a function of radius. This is more due to the accretion shock during assembly history of galaxy groups. While in the center of this groups and clusters, you see the elevation of of core entropy. So what's the reason for that? I mean, both cooling and heating processes in the core can actually help elevate the entropy. But the more important thing is that if you look at the distribution of the entropy in the core, you see a bimodality. So we don't know what's the reason for that. Another challenge is the breakdown of self-similar scaling relationship. We see that in this plot, that this is the luminosity, X-ray luminosity against the temperature. Temperature is related to the mass according to the Vero theorem. So higher temperature just means more massive systems. So on the cluster scales, again, it fulfills a strict power law, but it breaks down at 1 keV level. So what's the reason for this breakdown? So usually 1 keV is where we distinguish groups and clusters. So an example is this paper. So Arif Babu is my master's supervisor when I was working in University of Victoria. So we do this study by using cosmological simulations. There are two popular solutions for the problems that I illustrated in the previous slides. One is the stellar feedback, the other is AGN feedback. I need to be very careful, so I'm not saying that there exists no other form of feedback, but these two, in order to solve those major problems in groups and clusters, these two in cosmological simulations are the most popular solutions. So in our simulations, we basically do not include the AGN feedback. One reason is that we don't know how to properly model AGN feedback in cosmological simulations, given the limitations in our simulations. And the other real reason is that actually we don't have enough time to include that. And the other one is the stellar feedback origins from the supernova feedback. So we want to study if we do, in cosmological simulations, we do not include AGN feedback from the galaxy, what will happen to the observed property of galaxy groups? And if the properties fail, so we fail to produce those observed properties, then what's the reason for those failures? And whether we can constrain the nature of the AGN feedback from this study. Now, basically, our stellar feedback, stellar star formation-driven wind, we implement that wind in our simulation based on the momentum-driven wind model, which is initially proposed by Murray, Cote, and Thompson 2005 model. So basically, we know that the explosion of the supernova, the cooling the energy might not be conserved because the cooling could be very fast from the supernova explosion. So, but the momentum can be conserved. And the other thing is that the UV photons from the massive stars, which do not go into the supernova feedback, the momentum from those photons is an negligible amount compared to the amount produced by supernova explosion. So there are two different sources. The UV photons actually can be absorbed by the dust grains in the intercluster medium, and dust grains, through a simple analytic calculation in that paper, it is well coupled to the gas. So dust absorbs the momentum from the UV photons, and it is coupled to the ISM. Then through that mechanism, the ISM is driven away by the momentum. So prediction from that model is that wind velocity, wind ejection velocity in our simulation is proportional to sigma, which is the velocity dispersion of the galaxy. So larger system, according to Vero theorem, a more massive system have larger sigma. And also that is the thing, the mass loading factor, which is the wind mass loading rate divided by the star formation rate of of the galaxy is inversely proportional to circular velocity of the galaxy, or you can say that it's sigma. So Hopkins 2012 is high resolution simulations, which is zooming simulations on single galaxies. So it's this power law depends on the power index depends on a lot of factors, including the mechanism, the specific mechanism that drive those winds, as well as those galaxy types. So you see a very large scatter over there. But according to astronomical precision, this is enough. It's close to enough to -1. So we implement this wind model to the cosmological simulations, and Romeo Davey and his collaborators has achieved a lot of success in reproducing a wide range of observational features on different scales over the years. So we think that the momentum-driven wind model is the best way for the galaxies that are interesting to us. So this is the detail of the simulations that we run. It's a standard 100 megaparsec box with 576 cube dark matter and SPH particles. So we include the cooling from primordial gas and the metal cooling, and we adopt a Chabrier initial mass function. We use the momentum-driven stellar-powered wind, and we also include the metal enrichment from the type 2, type 1A, and AGB. AGB is the late stage of those of non-supernova stars. So but we do not include AGN feedback in the simulation. So this is the first interesting thing. So we compare our simulated results with the observations from the top to the bottom panel. Is the baryonic mass fraction, hot gas fraction, stellar mass fraction, cold mass fraction. So here on the left-hand side is the Redshift 0 result, and on the right-hand side is just the temporal evolution. So I'm not going into the details. On the right-hand side, the details are in that paper. But here, let's just focus on here. So baryonic mass is way much higher than the observed level. But interesting thing is that hot gas fraction is very close to that. But the star is like twice as many as being observed. So without AGN feedback, we definitely produce too much stars, too many stars compared to the observed level. So this is the galaxy stellar mass function. So it's just a number. So integration of this curve is just a number density of galaxy within certain mass interval. So we see that analytically we expect a Schechter formalism. Your stellar mass function should strictly fit this Schechter power law, but here at high mass end above 10 to the 11 solar mass. So this is the simulated result. So we see those peaks, and if we artificially reduce the stellar mass for those galaxies by 3 times, and now you see that it fits the analytic prediction very well. So the thing is that where those peaks come from, it actually so only the central galaxy in our groups failed. In those massive systems, maybe they also include one massive satellite, but in most systems, only the central galaxy fails. So why the central galaxy fail without AGN feedback? So before we move on, so this is this is a PDF version, so there is no animation. But here, the idea I'm trying to illustrate is that the gas ejected from the galaxy does not leave the galaxy forever, but we see those galactic fontaines. We have, in cosmological simulations, we do see that gas ejected at earlier epochs do return to the galaxy at later time. So this is the turnaround radius of those gas particles. So you can see there's a redshift dependency. So at high redshift, it's way more easier to eject material far away from the galaxy. So that's why we observe that many metals in the intergalactic medium at high redshift. So at low redshift, it becomes way harder to get out, for the wind particles to get out of the galactic halos. So here, this is the background knowledge. So how do galaxies get their gas? So we have 3 different modes. It's cold mode, hot mode, and wing mode. The hot mode is a standard scenario where the gas is shock heated to the zero temperature of the halo and then cool down and feed the galaxy. Cold mode is through the filaments. So the gas in the filaments never ever shock heated to the zero temperature, but they can, in low mass system and high redshift, it's way much easier to feed galaxy through these filaments rather than the standard hot mode. But this scenario has been updated by Oppenheimer et al. 2010. In a low redshift, they created a new wing mode. So the stars at low redshift is mainly formed from the materials that have been previously ejected from the parent galaxies. So it gives you a scenario what's happening here. So that is the thing. So we basically track the star and the gas particles in the central galaxies because they fail, right? So we track those particles through the entire history of in the simulation. So we want to know where those cold components come from. So red curve here is the standard overcooling particles. It's the cooled IGRM. So these particles, they have been shock heated to the hot phase in the groups. But here, this black curves, they represent the amount that has been brought into the central galaxy through galactic mergers. So actually, we see that we don't see over a cooling crisis, as most people has claimed, but actually in our simulation, the central galaxy failed without AGN because the massive satellites has brought too much amount of cold gas into the groups. So the first claim, the first strongest claim in our paper is that this gives you a constraint to the nature of AGN. So you have to eject the gas at the very, very early stage before those satellites can bring cold gas into the central galaxy. Not AGN, the gentle jet-like AGN feedback at low redshift is not effective in removing those gas because you basically cannot remove gas from the central galaxies out of the group potential well, but you have to move those gas from early age before these satellite galaxies merge into the group halo. We also studied the scaling relationships because these scaling relationships, for example, the luminosity against temperature or the luminosity against mass or the entropy, they give us many constraints on the feedback models. So you can compare these scaling relationship with the observations. So actually, without AGN feedback, our scaling relationships fit the observation pretty well. So that's the problem. So a lot of people, they claim that they compare their AGN run and no AGN run. They claim that the improvement they get in reproducing those properties is due to their AGN feedback. So that's not the thing that we support. So we are against that. So we are a bit more conserved. So we think that there must be other reasons. Sometimes you can produce the right features with the wrong physics. It's totally possible. So we just state that a lot of people might have overclaimed the significance of AGN feedback. Another constraint that you can compare to the observation is the matter enrichment. It's very interesting. We produce twice as many stars as observed, but we produce the right amount of metals in the hot gas phase. So what's the reason for that? So we compare the mass-weighted, emission-weighted metal abundance of hot halo gas with the observations. They all fit the observations pretty well. So what's the reason for that? So we studied the detailed distribution of metals within the group. So this is the radius. So we see that at very large radius, our data actually fits the observation pretty well. Only in the most central regions, within the 1/10 of 500, we produce 3 times more metals than observation. But because of the volume is too small, so the overall amount of metal is still very comparable to the observed level. So within that radial beams, the majority of the metals actually come from the central galaxy, which is represented by the red segment. Here, this is the different components from the central galaxy, satellite galaxy, external, and the unbound field stars in the intracluster light. So basically, metals that are located at different radii, they're fractional contribution from different components is different. So probably our central galaxy have like produced too much metals, but majority, I can say 80 or 90% of the metals produced in the central galaxy actually return back to the central galaxy. So most of the metals are locked in the cold gas phase or in the stars in the central galaxy instead of being ejected in the hot phase. So the hot phase is still not that polluted. So here is the thing. So we know that in how to properly model the galactic wings is difficult in cosmological simulations because we don't have that high enough resolution, and it won't be. This problem will last in the next maybe 10 years because we basically cannot expect our computer supercomputing power to reach that level. So still, in the old wing model, we discovered, that a lot of like wing particles from the massive galaxy, they actually have not escaped from the halo, but because of the hydrodynamic effect, once it is the wing particles is coupled to the SPH particles in the environment, it falls back very fast. Then it's not a realistic wing, so we didn't model the wing properly. So now we use the new wing model and see what's happened to our simulation. Now the old failures is resolved by changing the wing model. So now we have a better scaling in modeling stellar powered wing, and you'd see that even those missing barium problem is largely solved by using the right, better wing model. So the problem is that do you still need AGN feedback? So we only include stellar powered wings, and we solve a lot of problems. So you see the details of the stellar mass function. This is the old plot, and this is the new plot. So here, this is problem. So the depth here in the intermediate mass range actually indicates there's still some problems. Probably still some problems in the wing model, in the stellar powered wing models. But the point is that we already the problem that previously exists is probably because we didn't model the stellar winged very well. So a lot of people think that this improvement is due to AGN feedback. This probably is not. It's not safe to say that. But the other thing I want to point out is that we previously successfully reproduced the X-ray scaling relationship, which is the selling point of the old runs. But here, once you change the SPH schemes, for example, you include the artificial thermal conduction and also the turbulent mixing processes in the SPH things, and it will change the X-ray properties hugely. So now the thing is that our previous success is facing a new challenge by adding more new physics. So I directly go to the summary. So the thing is that the old model, which probably does not include the right stellar powered wing model, is successfully reproduced the X-ray scaling relationship, but the central galaxy failed. The reason for that failure is that it's not because of the cooling crisis in the core, but actually because of the massive satellites have merged too much amount of cold gas. So if AGN is playing a role, AGN should be able to eject those cold components at very early stages before those galaxies merge into the groups. The third thing is that SPH scheme and the detailed implementation of supernova-driven wind in cosmological simulations will definitely affect the X-ray scaling relationships on the group scale. So even with the wrong physics, you can produce the right observable properties. So that's the point. The last one, which is the strongest point in this talk, is that the significance of AGN feedback might be overclaimed by some early people doing AGN simulations. Okay, so that's all. Thanks.
Thanks. Any question?
The question is, there is some constraint in the mass of the number of galaxies in your group that you consider to the plot that you show the metallicities cross to the radius. Yeah. There is some constraint that your simulation works, or in terms of the number of
Yes. So in 2008, there's an early paper on group which is done by Romeo Davet. So he compared the alpha to ion ratio in the hot gas, and with and without galactic stellar-powered galactic wind. This alpha ion ratio differs a lot. Only can you enhance that alpha ion ratio to the observed level by using energetic outflows from galaxies. So that gives you a constraint, because without like these outflows, you enrich the hot gas by the intracluster light, these few stars, then the alpha ion ratio will be very, very low, because you only have the type AGB, the mass loss from AGB stars, the delayed type 1a feedback. So it's the dominating mechanism to enrich the hot gas. The thing is that the ISM, the alpha ion ratio in the ISM, is way much higher than those mechanisms. So that gives you a constraint. There must be outflows happening there. So we have to bring high alpha ion ratio to further regions. So that's the constraint. The amount of metal is abundance. Metal abundance is also notoriously hard to simulate, to reproduce, like at least 10 years ago, because there are a lot of reasons. I mean, the yields from supernova has a large uncertainty. The ion abundance from type 1a supernova, as far as I know, have like as large as 50% of the uncertainty. So even, I mean, maybe in the simulations something goes wrong, but because of that uncertainty in your yields, you still can reproduce the observed metal abundance. So it's, I mean, we have to get bread and butter, right? So yeah.
Other questions? Okay, thank you again for the talk.
Okay.
Okay.
Doesn't matter. Okay, thank you.
The next speaker is Francesca Loi from the University of Cagliari.
Okay. How many of you knows that there are magnetic fields in galaxy clusters? No. Okay. So there are, and today I will try to explain why there are magnetic fields in galaxy clusters. As you know, galaxy clusters are the largest gravitational bound systems in the universe. Their major components are dark matter, luminous matter. There is atomic plasma that permeates the cluster volumes, and it emits through the Bremsstrahlung process in the X-ray. And then, if we observe galaxy clusters in the radio regime, we can find radio galaxies that are just galaxies where the active galactic nuclei at the center emit relativistic particle and magnetic fields, and the interaction between these two components is the synchrotron process. So if we observe this object, we can find a strong linearly polarized signal. But in some galaxy clusters in the radio regime, it is possible to detect a diffuse emission. This emission is called radio halo, and these sources are synchrotron sources. So these are the direct proof of the fact that there is an intracluster magnetic field spread in the galaxy cluster volume, and also a relativistic particle population. So my work is to try to constrain the properties of these magnetic fields. How is it possible? We can use the Faraday rotation effect. I think that most of you knows this effect. is not just an astrophysical effect. But in astrophysics, here, what happens is that if I have a powerful radio galaxies in the background of a galaxy cluster, I know that the radio galaxies emits a strong linearly polarized signal. So when it passes through the magnetized plasma of the galaxy cluster, its polarization plane rotates, and this rotation depends on the wavelength, but even on this constant that is defined as the integral all over the galaxy the cluster length of the thermal density times the line of sight parallel component of the intracluster magnetic field. So what we can do with the Faraday rotation effect is just to choose a powerful radio galaxies, background radio galaxy, and we observe it at different wavelength. Then, for each line of sight, we fit this relation. At the end, we find an image of the rotation measure. This can be seen as an image of the magnetic field inside the galaxy cluster. Okay? If we have measurement of the thermic plasma, in some way we can get the measurement of the magnetic fields. Okay? So this is a really powerful method, but you have to have the background radio galaxies. So you can do this just for a small portion of the cluster volume, cluster area. So what could be better is to observe radio halos, to try to do the same for this object, because they are usually spread all over the cluster volume. So if you can apply the same method with radio halos, you can have an image of the magnetic field all over the cluster, okay? But there are, of course, problems. In fact, the first problem is the differential rotation inside the frequency band. Because imagine that you are here, your radio telescope is here, and here, there is the emission of strong polarized signals. The problem is that these signals pass through a different length of the magnetized plasma. So the rotation is different. And the sum is incoherent. So basically the degree of polarization is lower. And we have the same problem with the beam depolarization, because if I have two strongly polarized signals inside the same beam of the telescope, the degree of polarization is lower. So these effects are really important and are quantifiable just with numerical simulations. The goal of this work was to understand if what is the intrinsic degree of polarization of radio halos, because these sources are thought to be, in literature, it is thought that these sources are unpolarized sources. So if they are unpolarized, we cannot use them to constrain the magnetic fields. So the first question is, what is the intrinsic degree of polarization of radio halos? And then, next generation radio telescope could detect their polarization. So, what are next generation radio telescope? The SKA, the Square Kilometer Array. This is a very huge project. It involves not just radio astronomers, but a lot of scientists from all over the world. And in particular, I'm interested in the SKA-1 that is the instrument that will be built in South Africa. And as you can see here, these are the 5 key projects for the SKA. So probably many of you, cosmologists or other people, can be interested in this instrument. Okay? And as you can see, there is even the cosmic magnetism to try to understand why there are magnetic fields in every scale of the universe. So, how can we reproduce radio halos? As you know, in the standard scenario of hierarchical formation of the structures, galaxy cluster grows and form through merger event. That could be the collision between two galaxy clusters. And radio halos are found in this turbulent environment. Okay, so we need cosmological magnetohydrodynamical simulation to reproduce this system and so to reproduce the radio halo. Thanks to a collaboration between the Los Alamos National Laboratory and our astronomical observation in Cagliari, I had the chance to study this an event, a collision between two galaxy clusters that lasts 2 gigayears approximately. And basically, they give me some physical cubes with properties like the magnetic field, the density, the temperature. Then I use the Faraday package to obtain the X-ray emission, the radio emission, and the rotation measure image. Okay, so for what concerns the X-ray emission, we know that the surface brightness in X-ray, it depends on the thermic plasma density and the temperature. So with this software package, I perform this integral for each line of sight, and this is the result. You are observing two galaxy clusters that are colliding with a speed of 3,000 kilometers per second. These are really violent, energetic processes. They can release a high amount of energy in the intracluster medium. They can hit the gas, as you can see from the sharp discontinuities in the X-ray images. Yes, of course, this event can accelerate particles. There is a lot of physics here. Okay, then I compute the radio emission that depends under some assumption on the magnetic fields. And this is the result. As you can see, it has the emission as a filamentary structure. And as the two galaxy clusters collide, the emission is brighter because the particles have been accelerated by the shocks. And even the magnetic field is amplified. So this is the emission, the total intensity emission. But then let's go to the polarized emission. That is the thing that I care most. Yeah, what we have to compute is the effect that I was talking before. The fact that if there is a polarized signal emitted in a certain position of the galaxy cluster, it has to pass through the galaxy cluster length. So it receives a rotation due to the Faraday rotation effect. So we have to rotate each signal depending on the rotation measure of the position of the emission, and then we obtain the polarized signal. These images are really important because they tell us that intrinsically the radio halos are polarized. Okay? So they are polarized. This was the first question. They have this degree of polarization. I just plotted here just the last stage of the collision. And if we will observe a system like this with the SKA, so with a noise of 1 microjansky per beam and with a resolution of 10 arcsecond, we still detect the polarization. So this was the second question. And look, for the literature here, you cannot see anything with an instrument now. So this is a really impressive result. But there is something that I have to tell you, because due to the Faraday rotation, even in the band of frequency, if I have a polarized signal, I can see a different degree of polarization because the signal is rotating inside my frequency band. Okay, so I should see something like this. Here is the flux times the wavelength squared. But the point is that if I just average the signal over the whole band of frequency, the degree of polarization is lower. Okay, it's always because of the Faraday rotation. So I have to use some technique to recover the missed polarized signal, and this technique is the rotation measure synthesis technique. The idea, simple word, is to assume that to try a range of values for the rotation measure. So I take each channel and I try every value of the rotation measure. So and I derotate the signal. At the end, what I can find is a polarization, these red lines, at a given rotation measure values. So basically, I'm trying to understand which polarized signal, at which polarized signal correspond a given rotation measure. So why numerical simulations are important? Because I can apply this technique, but I can check if this technique is working or not. Because it is not clear if I have to take the rotation measure values of the maximum of the polarization that I can find, or the largest displacement with respect to 0. So thanks to the fact that I have numerical simulation, I can check and I can find if this technique works. So I've done the same for band 1 and band 2, and at the end I just want to show you this result. So instead of having just a small portion of the galaxy cluster, I have a larger image of the rotation measure. So I can, I basically, how can I say it? Yeah, the statistic is higher here because I do not have just a small portion, but a larger area of rotation measurements. So at the end, the conclusion are that radio halos could be intrinsically polarized. Next generation telescope could detect their polarization, and halos, as you can see, are brighter here in the band 1 because, as I told you, they are synchrotron sources. So the lower the frequency, the higher the flux, the brightness. But they suffer more in band 1, the Faraday depolarization. Okay. So another conclusion is that rotation measure synthesis can recover part of the intrinsic polarization. The resolution is higher with band 1, as you can see here. This is called the transfer function. If you are curious, I can give maybe more detail on this. But with band 2, we recover more polarized signal. Here, this plot is the plot of the degree of polarization. It's higher here than in band 2 than in band 1. So that's all. Thank you.
Question? No question?
If I remember, there are like 54 radio halos that have been discovered. Yeah. So the question is, how many of them has these magnetic fields? I mean, yes, I mean, the message that there are these magnetic fields that you can feel in these radio halos. There is this connection. Or not?
Yeah, the point is that you analyze basically the spectra of these radio halos. You find that they have a power law spectra. This is typical for synchrotron sources. So you end with the conclusion that they are synchrotron sources, so they are made by relativistic particle magnetic field. So there should be a magnetic field spread all over the cluster volume.
So the question is, what is the relation between the radio halos and the galaxy cluster itself? I mean, there is something there or not?
Okay. Yeah, there are statistical studies about the mass of galaxy clusters and the brightness of radio halos. I'm not an expert on this, but there are some relations, but they are still investigated because with the instrument that we have now, we don't have a big statistic. There are really few radio halos detected by now. I mean, not few radio halos. There are few radio halos. Just 2 cases polarized radio halos, polarization detected. So I don't know. There are, but
other question?
So I just have a question which might not be too related to the talk. So I'm interested in the level of turbulence in the intercluster medium. So through radio bands.
Mach number.
The reason I'm interested in that is because if we measure the mass of a cluster, for example, we have different methods. For example, the lensing, or we can use X-ray detection to assume that the gas is in hydrostatic equilibrium. But the level of turbulence gives some bias to the X-ray mass. Because there exists, we do know that there exists non-thermal pressure existing in the group 10 cluster, and the turbulence is one possible resource for that bias. So is it? So I'm just curious. So is there any observable constraints you can get on the level of turbulence through the radio observation?
Okay.
No, it's actually more related to the X-ray bands, but unfortunately the new X-ray telescope was done. So
You mentioned the discontinuities in the X-ray maps for galaxy cluster. Okay. Yeah, it's really challenging because it's hard to for many effects in physics, it happens that you have 2 things, and you have to disentangle these 2 things. So the problem, let's say in this way, the problem of the rotation measure is that you need accurate measurement of X-ray emissions, and so it is hard to disentangle this from the turbulent magnetic field from this study, because it's an interaction, so it's quite impossible to disentangle them. But if you are able to make really precise measurement, if you have a very good model for the intracluster magnetic field, of course you start from the magnetic field and you try to infer the X-ray distribution, so the thermic plasma discontinuities. Yeah, this should be really, really good, but we are quite far from this.
Other questions? Okay, thanks, Francesca, again. The next speaker is Camillo Del Grado Correal from the University of Ferrara.
Ciao, everyone. Okay. I'm a PhD student from University of Ferrara, but also from the Erasmus Mundus program. It's an international program between 6 universities in Europe. Also, I'm part of the Clash Build T program. It's a collaboration between Europe and USA. So I'm going to talk about the project that I'm doing in my PhD. The name is first I need to identify low luminosity, high redshift galaxies. Later I'm doing the understanding of physical properties. And the idea is use the power of galaxy cluster, the gravitational power of galaxy clusters. So this is a new concept that have been developed from the 90s when we put a whole space telescope in the space. Okay, I'm going to talk about the contest. Later I'm going to describe the project. So the contest begins with the sky. I mean, Van Gogh, see the galaxies. This is amazing because he noticed that there's a galaxy here. This is his representation. No? I mean, the galaxies, there is some trace also before, no, in Galileo identified the Milky Way, and the galaxy was in the mind of people, also was the measured objects at the same time that Van Gogh. So the galaxies are there. Also, Van Gogh talked about something about the network of the stars, that maybe there is a relation with the cities, and nowadays we know that the galaxy cluster are the central point in this cosmic web. So at the end has some reason. This is our instruments in the optical and infrared that we have and we are going to have. So we have now, for example, BLT. We have our friend Hubble. This is James Webb. It's going to be launched very soon. This is the big telescope that is going to be built for the European Union. So these are our instruments in optical and infrared to see the faintest galaxies in the universe. So the idea is that we can use the galaxy clusters as a cosmic lens to go deeper. This is the important message for this talk. Hubble was 25 years old last year. I'm from Colombia. We are a developing country in astronomy. And I mean, the importance of Hubble around the world is just, this was a handout, and also I wrote to the most important newspaper in Colombia. So the news of 25 years old, the Hubble that we put on the space, and we got the first images on the space. This is a really important advancement of the humanity. So I think after the landing of the men over the moon, I think the second achievement that we have is this Hubble. So this is one of our results in our group, that there was predicted when the new image of a supernova was appear. So by using the observation done, this is the multiple image associated with the supernova, with the lens effect, strong lensing effect with the galaxy. Later, there was we could predict that there was appears other image of the supernova, and there was before others one here. So this is an effect that is called Shapiro time delay, and this is something that we did by using Hubble. I'm going to explain more in detail, but just to say that the power that we have with Hubble. So this is other example that we did with Hubble. At the beginning, 90s, before it was the Hubble put in the space, we have this limit in the enrichment. I mean, goes just until this time, Redshift 1. But later, when there was appears the first Hubble deep field, we go deeper, and with the Hubble ultra deep field, more deeper. And later, with the infrared cam, when was put in the Hubble, we go deeper also. And with our project with Clash, by using lensing, we go more deeper. We are reaching around 500 years, million years after Big Bang. And we hope that with the James Webb, we are going to go more deeper to understand something that is called the time of reionization, and also how was the first galaxies and first stars formed. The idea is that we need to understand how was reionization this part of the universe. We have just around 10 galaxies over from redshift 6 to 10. So we need to increase the sample to really understand how it works. So we need to, of course, wait for James Webb, but for a while we can use the galaxy clusters as a lens. This is in this map we can see how was the star formation rate across the universe. So you can see how it was increasing across the time. There is a peak around redshift 2 to 3 here, and later was the decreasing. So we need to count. We need to count these galaxies at different redshift and also different mass and different luminosity regime to can finish this plot that tell us the star formation rate across the universe. So this is this can answer our fundamental question that how was formed us now at the end. So this is my project, and this is the people that I'm working. Piero Rosati is my advisor. Gabriel Cameni is a postdoc in the university. Claudio and Gabriel, they work on the lens model of the galaxy cluster. Amata works on the photometric catalog with the HT, have 16 filters. Italo was working with the BMOS catalog in BLT. Mario and Italo get the spectra. And Eros, he's an expert in high-redshift universe. So they support my work. I mean, they are my advisor in general. And this is my project. So we have 25 clusters. Photometric information by HT is around 1,000 hours. And with BMOS, BLT, we have the information of 13 clusters. I mean, the yellow square are the cluster that we have a spectroscopic confirmation of the member clusters and lessened galaxies with BMOS, BLT. And the others, we have the other 25, we have the photometric information, photometric catalogs. Here you can see the BMOS, is here. This is BLT complex. And also we are using MUSE, the new spectrum that I'm going to talk about. With BMOS, the program was 230 hours. It was the range in the two bands, and this is the slits, because in this case with BMOS, we use slits and we get the spectra. In the case of MUSE, we have for every pixel we have a spectra. So this is the general context. Now we have our telescope here. We have the galaxy cluster. We have the galaxy, and for the effect of there is a bending of the light. So we have three effects. One is the magnification of the flux, but the brightness surface is keeping by lensing. So it's invariant by lensing. So if the flux increase, the area decrease. So this is calling, we can call galaxy cluster as a focusing telescope, because we can magnify order from 5 to 50 the flux, the intrinsic flux. Also there is the multiply images that we can see. And the other important effect is the magnify, and okay, there is the deformation of the form of the galaxy. No? So the model that we can build is by using the spectroscopic members and also the families that have been lensed. So with this information, we can predict what was the positions, and this is a fitting model. We have the prediction of the position of the lensed galaxies, and we have the identification, the spectroscopic identification of the lensed galaxies by the cluster. And later we can get the mass density profile of the cluster, and later on we can do these magnification maps. So in every point you can see, it depends on the redshift, of course. And for example, redshift 2, redshift 4, redshift 10. So we can get the redshift of the lensed galaxy. Later we multiply with the magnification in each case, and we can get the intrinsic luminosity value of this galaxy, of the lensed galaxy. So we can build this plot that shows, this is important plot because in this part, this is a campaign Lefebvre that is a deep and ultra deep survey by using BLT. So they put just the telescope, there was the field, and they found that there is a limit of this is absolute magnitude in UV. This is related with the intrinsic luminosity. So there is a limit that you can reach. Some the deep objects are here, and when you put the galaxy cluster there, you can go deeper, and you can, and in some cases, you can go to this is the limit Hubble, this F, this is a filter and red filter in the whole space. And this is magnitude 30, this is the limit that you can reach with the Hubble. And in terms of number, these 5 magnitudes correspond and 100 times the fluxes. So by using the galaxy clusters as a cosmic telescope, we can reach 100 sources that are 100 less fainter than the ones that just we use the telescope. So it doesn't matter the optical instrument that we have. If we put a galaxy cluster in the line of our observation of the galaxy, no, that we are going to be interested to understand the physical properties or other things, we can go deeper and fainter. Also, this is a competition. This is a competition here because there are some cases that this is by using. This is the case of COE. This is by using a cluster. But there is a competition between the fields by using big telescope like Keck, and by using focusing telescope. I mean by using the small the Hubble and the galaxy cluster to get the long distance galaxies, but in the range of deeper galaxies and fainter galaxies, the galaxy cluster as a cosmic telescope is win. Now, this is part of the message. So now we have data from MUSE. MUSE is a revolution in astronomy. It's part of the second stage of the instrumentation at BLT. It's called integral field spectroscopy. The field view is 1 arc minute. We have this is the range. This is the range of wavelength. In terms of this power resolution, when you see the spectra, is you have a 2.3 Armstrong. I mean that you can define very good. And this is the idea. You have for every pixel you have a spectra. So you have around in this range wavelength. You have around 2,300 slides to say it in this plot. So you can get for a pixel the spectra, and in this case, this is some families that we found. Identification different chemical elements here, the molecules, and also we can go to the core of the cluster and identify more families. For example, in this word, this cluster is 0416, we identify more families, so that the other words before, and the other cluster also. So if we increase the number of lenses families, the model is going to be better, because the prediction magnification must, because you are going to have more you have more member families, so you have more numbered to predict the position that can be correlated. So now we did this work in J0416, and now we're interested to understand the clusters to 1206. Here, for example, there is some description of the extraction of the spectra. So we use a spectra aperture of 0.8 arc second. In this case, we have two galaxies. We already select from the photometric catalog 400 galaxies. And of course, there are 400 spectra, but not all are. We have just 4.5 hours in Muse. So there are some sources that can be detected very well. And for example, in this case, you can see the spectra with Muse. This is a early type galaxy, and you can be defined this spectroscopic line that defines the whole stellar population. And this is the counterpart, the photometric counterpart. So you are going to get in the redshift, because we need we need to identify the member clusters and also the lensed galaxies. The error in the redshift is 10 to minus 4 in this case. And also we have this is a zoom of the same galaxy. You can see how really well defined. We have this other. This is a spectrum of a star-forming galaxy, and it's also the quality level of the books. This is very good. And this is the magnitude here. This is the identification of Lyman alpha. This Lyman alpha lies at a high redshift, is 0.6. And after this Lyman alpha, we can understand some processes of ionization that are happening at this redshift. So this is important to identify this Lyman alpha. And getting the physical properties of the region, we can understand if there is some gas that is outflowing or inflowing. And this is the next step, but this is combining the spectra and the photometric. And but you see there is nothing here, but in the spectra you can see how is. And this is the spectroscopy identification of the member clusters of the core of this cluster, the lensed galaxies. So we have early type and also star forming, and we have our lensed galaxies at this high redshift, and there are some sources that are faint in this case. That that the limit, the whole limit is magnitude 30. So there are these cases that increase our number of lensed galaxies at this high redshift. Now it's this is the searching. We are looking for to increase the number counts at this high redshift and faint level of the universe. So cluster give us this opportunity to go there. Finally, you can see how how is distributed in the image plane the different kind of galaxies that I found. So it's in the same image. So this is really a pity, because you have the image plane, and you need to deconvolve to say that in the 3D object, and later see where is the high redshift galaxies. So I put just to show how is the image plane. No? Grazie mille. Anyhow, I like this image because this is the castle in Ferrara, but this is a lake that is around the castle. So here we have we are watching the universe in this way, no? Actually, it's like lensing effect, no? So the image is related with the talk. Okay, thank you.
Any question?
Maybe I missed it, I don't know. But I was wondering what is the input going into the magnification maps that you make? Is it the deformation of the galaxies, or it's some information from the mass of the cluster? How are they constructed, these magnification maps?
Yes, the cluster effect, the cluster galaxies. So you can have a mass density profile, and you can get the magnification for this effect with the clusters. So this is important to have the member clusters. Also, we have information, I forgot to tell, but it was very important. We have X-ray information of the cluster. Because so with the lensing model, we can get the 80% of the density profile, the mass density profile of the cluster. With X-ray, we have the 15%, and with the visible optical counterpart, we have the 5%. So we can get all of the density mass profile, and with this, we can get the magnification. When we are doing the lensing model, the magnification maps appears at the same time. It's multi-parametric model.
Other question? Okay. Thanks, Camille, again.
Thank you.
Okay. The next speaker is Fabio Sciarrino from the University La Sapienza of Rome.
So good morning. First of all, thank you for the invitation. So I'm slightly changing topics, so no astrophysics. We are going, we use single photons inside the chip. So my purpose is to provide you an overview of this research field, not going too much into technicality, but I will still try to show you what is one of the last trends of research. So let's start from this picture from the Matrix movie, which somehow show information at the classical level. And we can quote Rolf Landauer, which was researched at IBM. Information is physical. This means basically that when you manipulate information, you are exploiting physics laws. In this case, we are exploiting classical laws. But we know that if you go at a deeper level, we have quantum mechanics. So one can try to change the paradigm and not using a Boolean logic, but instead of quantum physics as underlying logic to manipulate information. And this is where you have quantum information. So basically you are combining quantum mechanics and information theory. So this idea started in the 80s with the first contribution by Richard Feynman, by several scientists at IBM, and now it's a major research field with also many companies from information technology which are starting to heavily investigate in the research area. So what are the challenges of quantum information? They range from basic science to emerging quantum technology. So you would like to carry out fundamental physics, you would like to test non-locality, quantum contextuality, you would like to understand where is the boundary between the classical and the quantum worlds. But then you can also have a technological side. So basically you take any technologically area, you take the word quantum, you put the word quantum behind, you get quantum cryptography, quantum computing, quantum simulation, and the basic question is, by exploiting quantum phenomena, can I improve my technological ability? So my research contribution, where also INRiM is involved, is to exploit optics for quantum information. So basically we work in the visible range. What you need to do, you need to identify a specific electromagnetic field, This means you fix the wavelength, you fix the direction, you fix the polarization, you fix the time, and then you exploit single photons to encode information. When you encode the information, you can encode the information into the photonics degree of freedom. This can be the polarization of light, the spatial mode, the time being. So now what you need to have the capability to manipulate single photons, to generate single photons, to manipulate and to detect. Then you also want to transmit single photon states over large distance for quantum cryptography. And this research area started, I would say, in the 80s, and now you have many laboratories all around the world. But when you start increasing the complexity of your apparatus, you have some strong limitations. Because this is a typical picture of the apparatus. You have some problem of scalability. You need a lot of money to handle all the equipment, a lot of persons. You have problem of stability. And then, in the last few years, one of the main directions is to try to move these quantum labs inside the chip. And to this purpose, we want to exploit integrated waveguide technology. So you want to perform all this operation inside a single chip. And this is what I'm going to describe you. So the goal is to move from this paradigm to one chip where all the operations are performed. What are the applications of quantum information on a chip? We can have quantum computation, we can have quantum simulation, where the goal is to simulate quantum systems with another quantum system which is completely under your control. Then you can have boson sampling in something that we're going to describe shortly. You can have quantum walk, where you have photons which are walking inside the chip, and quantum walks allows you to simulate different physical phenomena. Then you can also have other area of interest. You can have quantum communication, where you want to send single photons from one space to another space over long distance. This can be done by using fiber links or by using free space communication. So in August, the first quantum satellite, the quantum Sputnik, was launched by China. They launched a satellite which goes is to send single photons from the orbit to the Earth. Then you can have fundamental science performed on a chip, and finally, you can address quantum metrology and quantum sensing. So now I'm going to describe you our research contributions. This is a joint collaboration between Sapienza, University of Rome, and Politecnico di Milano and CNR in Milano. So we are the quantum side of the story, since we have expertise in quantum optics, while Milano is involved in the fabrication of the integrated chip. So the idea is to have a chip where you can send light and you can manipulate single photons propagation. So the idea is to have a chip where somehow you have many fibers where light can propagate and interact. To this purpose, we exploit chips which are fabricated via femtosecond laser writing. What you do, you take a piece of glass, you tightly focus a pulsed laser inside the glass. The laser is inducing a permanent change in the index of refraction of the material. So if you go to Colosseum or to Eiffel, you can buy this piece of glass where you have a 3D reproduction of Tour Eiffel inside the glass. This is the same technology, but where you have a better control in how you are changing the glass structure. I'm talking about order of magnitudes. This is a typical movie, real time, where you have the substrate, the glass, you focus the laser from the top inside the glass, and then you are moving your sample. And by moving your sample, you are deciding which kind of geometry will have your waveguides. Now you can see a plasma. Again. If you see, you can see a spot, a white spot. This white spot is a plasma which is leading to the change in the index of refraction of the material. So you can see that the writing of the waveguides is very fast. And making this story very trivial, but you need to have a very precise control, and you also need to have a very excellent translation stage to properly control the waveguide geometry. What are the advantages? You can write waveguide with a three-dimensional geometry because you can move the chip in other direction, also up and down. This means that the waveguides can also go up and down. You can have a very rapid device prototyping. It's around 4 centimeters per second. You can fabricate your chip, and then you can test it. In our case, the fabrication is done by Siena in Milano. You take a fast train to Rome, it's 2 hours and a half, and then you start doing the quantum experiment. Then, if you have a proper engineering of the focus of the beam, you can have a waveguides which have a circular shape. This means that you can propagate Gaussian modes. To give you some estimates, the diameter of these waveguides is roughly 8 microns. So this is not nanophotonics, because your chip size is something like 8 centimeters, 5 centimeters. Another advantage is that it is very easy to send light inside the chip. So you can take an optical fiber, you put the optical fiber in front of the chip. If you properly align the chip, you can have an 80% coupling from the fiber to the chip. Then you will propagate in the chip, and then you come out again in the fiber. What is the first element that you would like to build on a chip? The first basic element is a beam splitter. You all know what is a beam splitter. How you achieve a beam splitter? You take 2 waveguides, and you route the 2 waveguides closer in the central part. Then, if you have light propagating here, it will be coupled with the other waveguide by exploiting the evanescent field. This means that the tail of these optical modes propagating inside this path will be coupled with the other waveguides. And then, if you engineer the distance between the 2 waveguides and the length of the central part, you can engineer the reflectivity and the transmittivity of the beam splitter. Then, by choosing an appropriate length of the beam splitter, you can obtain a beam splitter which is so-called symmetric. This means 50% transmittivity and 50% reflectivity. I have a question for you. How many of you know the Ongu-Mandel effect? 2. How many of you know what is a bosonic coalescence? 2. Okay, so this is 3. This is one of the most fundamental phenomena in physics, which is very easy and you should learn during your master thesis. So the idea is the following. You have a 50-50 beam splitter. You send 2 photons. So 2 photons, 1 photon here and 1 photon here. The 2 photons are indistinguishable. What means indistinguishable? Same polarization, time, spectral profile, spatial profile. I repeat, 1 photon here and 1 photon here. This is a symmetric beam splitter. This means that the probability of being reflected is 50%, and the probability of being transmitted is 50%. If you have 2 classical balls, we know that photons are not interacting. If you have 2 classical balls, you would expect that if you send 1 and 1 here, what you can get in the output. 2 ball here and 0 ball here, 1 ball here and 1 ball here, and then 0 ball here and 2 ball here. We agree on that. Now, if the 2 photons are indistinguishable, they will always come out together. This means that if you send 1 photon here and 1 photon here, you will always get on the output either 2 photon here and 0 photon here, either 0 photon here and 2 photon here. This means that the 2 photons agree where they should come out. But the photons are not interacting. Someone does not trust me from the face. But there is one point. Photons are indistinguishable particles. This means that the wave function must be symmetric. This means that the symmetrization of the wave function somehow allows you to have a kind of interaction between the 2 photons. And this phenomena, which is called bosonic coalescence, is maybe the first quantum optics experiment that cannot be replicated with a semi-classical model. The two photons must, however, be completely indistinguishable. And this phenomena was first observed in 1987 by Hong-Wu Mandel. It is not easy to generate two indistinguishable photons. So I repeat, you send the two photons and they will always come out together. So how you can do this experiment? You need to have photons which are indistinguishable. How do we generate indistinguishable photons? We create pair of photons. You have a nonlinear crystal. You shine a laser on a nonlinear crystal. You have a nonlinear interaction, and you create the red ball, which are pair of photons, which are always created together. Now we go back to the experiment. What we did in our experiment, you have a beam splitter. You have a nonlinear crystal here. You create pair of photons, one photon here and one photon here. You inject the two photons inside single mode fiber. One is here and one is here. Then you connect the single mode fiber with the beam splitter. Light interfere in the beam splitter. Then you come out. You have two single mode fiber, two detectors, and you measure the coincidence. And what do you observe? This is a typical picture of an apparatus of quantum optics. You may see the labs here at INRiM. This is what you measure. So you measure the coincidence. And this is a measure of the coincidence measured versus the temporal delay between the two photons. So imagine that now that the two photons have a temporal delay equal to 0. When they arrive in the beam splitter, they are interfering. They will always come out together, 2, 0, or 0, 2. Since they are always together, you will never measure a coincidence where you have one photon here and one photon here. So as you see from this plot, the number of coincidences is almost 0, because the photons are always coming out together. Now what you start doing, you want to have a transition from a quantum interference to the classical domain. What you do is that you have a delay line here. You delay one photon versus the other one. And what is the typical length is the coherence length. When the two photons are delayed, they are no more indistinguishable because the times give you the information on which photon is arriving. Now they behave like two classical balls, and what you see is that the coincidence go up. This is called the Hong-Wu Mandel dip, and this is the signature of the bosonic coalescence. So this tells you that the two photons agree where to go. So then what we did in the last few years, we implemented many other devices on a chip. We did much more complex networks. How much time do I have left? More or less. I don't know. 15, okay. So now what I would like to show you is a much more complicated Hong-Wu Mandel effect. And this is called boson sampling. So when you say boson sampling to someone, they always think to Higgs bosons. No, we are quantum optics. And the goal of boson sampling is to achieve the regime of quantum supremacy. So I would like to tell you what is first quantum supremacy. This term has been invented by a very famous theoretical physicist at Caltech, and it's called quantum supremacy, the regime where an experimental quantum technology will be able to outperform any classical technology, at least for a specific given task, even if useless. So what is the idea? You would like to have a computational problem that you can solve with a quantum hardware in a way which is much more efficient than any other classical hardware. So you can have many problems, but you would like to find the simplest problem where you can have this kind of regime of quantum supremacy. And the boson sampling problem was introduced by two computer scientists, Arkhipov and Aronson, in 2011. They are two computer scientists from MIT. Aronson is one of the most clever genius currently in computer science. He has a very nice blog on computer science. And the idea of the boson sampling is the following. It's to find out a very simple structure that is, let's say, easy to do experimentally, but which is extremely hard to do with a classical computer. What is boson sampling? It's the following problem. You have n bosons, which are non-interacting particles. This can be n photons. You have photonic networks of m optical modes where light propagates. The number of modes is much larger than the number of photons. And then what you do, this is a random structure. This means it has no symmetry. It's random but known. Bosons propagate in the structure. And your goal is to detect the output states. So your goal is not to calculate what is the output states. Your goal is to sample events from the output distribution. So you have a kind of dynamics that will be characterized by some evolution. And what you would like to do is to generate events according to the output distribution of such problem. And then we have one question. Is this problem easy to address if you have a classical hardware? And then is this problem easy to address if you have a quantum hardware? So let us first consider what can do a classical team. A classical team will try to do all the calculation. Let me show you. So if you have a classical team, you need to calculate the output state. Since you have n bosons, you need to symmetrize the wave function. And in order to symmetrize the wave function of n photons, you need to calculate the permanent of a squared matrix. Do you know what is a permanent? A permanent is similar to the determinant. It's the same formula, but when you have a determinant, you have to change the sign according to the permutation. So if you have a squared matrix ABCD, the determinant is AD minus BC. The permanent is AD plus BC. But now it turns out that calculating a determinant, you have many efficient classical algorithms. Instead, if you want to calculate the permanent, this is a problem which is extremely hard classically. It's called sharp P problem, which means that the complexity increases exponentially with the dimension of the matrix. This means that if you want to do this simple task on a classical computer, the complexity increases exponentially. To give you some number, if you have already 8 photons, and 100 optical modes, this is already not out of reach for a laptop. Instead, what you can do if you have a quantum technology, you simply do the experiment. What you do, you take n photons, you fabricate your network of m optical modes, you let the light evolve in the chip, and you detect the output states. And this can be done with resources which scales polynomially with the number of photons and the number of modes. So this was the proposal in 2011. In 2013, 4 different teams, this is our contribution, implemented the first proof of principle boson sampling. So what is, again, let me summarize, what is the goal of boson sampling? You have n photons, you inject the n photons in a unitary transformation acting on m optical modes, and your goal is to sample from the output distribution. So how you can implement this transformation acting on m optical modes? Basically, you need a large number of concatenated interferometers. So what you see here, this is an array of Mach-Zehnder interferometer, of many beam splitter and phase shifter, and these networks implement your transformation. This will be very demanding to achieve if you use standard lab optics instruments. So the goal is to have this transformation implemented inside the chip. So what you do, you have your networks of interferometer, and what you are simply doing, you are implementing these networks inside the chip. So you decide the unitary transformation that you would like to implement, you decompose this unitary transformation as many beam splitter and phase shifter, and then you fabricate your chip. So now I would like to show you what means doing a boson sampling experiment from a very experimental perspective. I told you you want to have single photon states, and you want to inject single photon state inside the big splitter. So first, you need to generate quantum states of light. We will generate, as I told you before, pair of photons. So what you do, you have a laser. With the laser, you excite a nonlinear crystal, and you generate pair of photons. In this movie, we are generating two pair of photons, which means 4 photons. The photons are the yellow ball. You have 2 here, and 1 photon is going here. This is a trigger detector. The other 3 photons are in these 3 optical fibers, and what you would like to do, you would like to synchronize the 3 photons, because you want the photons to be indistinguishable. They must arrive at the same time. So what you have some delay line, and you change the delay line to synchronize the 3 particles. Now that you have the 3 particles synchronized, you go again in a single mode fiber, and you have your integrated chip. Your integrated chip is your unitary transformation. So you have a recipe where one gives you the problem to solve, you go on the lab, you fabricate the chip, and now you have these yellow balls propagating inside the chip, and this movie gives you the idea that you have a quantum process. This means that you have a superposition principle. Light is evolving as a superposition of the different paths. And then finally, the output states, it's again connected with the fiber arrays, which connect you to single photon detector. So you have a bunch of single photon detector, which can count either 0 or 1. You measure the coincidence between the single photon detector. So basically what you are doing, you are sampling from the output state. You generate a quantum states, you measure it, each time you get different events from the collapse principle and so on, and you collect all the information. And so in your computer, you are registering all the events which reproduce the boson sampling dynamics. So this is what we did in the last few years. This is a boson sampler where you have 3 photons propagating over 13 modes. This means that the dimension of your Hilbert space is something like 300. This is not enough to have quantum supremacy. You can do this calculation in a very primitive mobile phone. What we need to do, we need to increase the number of photons and the number of modes. So if you want to have the regime of quantum supremacy, you need 10 photons and 100 modes. To have 10 photons and 100 modes, what do you need? You need more indistinguishable photons. These are called single photon sources. You need more complex chip. You need single photon detectors. And then you also need to address several fundamental theoretical issues. So what are the perspectives of the field according to this description? Each time you would like to do quantum information, you need to generate quantum states, you need to manipulate quantum states, and you need to detect quantum states. So now you have many groups which are working in the integration of single photon sources on a chip, manipulation of large integrated networks, and finally, single photon detector at the end. So this is a summary of our research activity. Today I focused on boson sampling to give you an idea of what it means doing quantum information on a chip. We are also working on quantum simulation, and we have also recently introduced a new device with a 3-dimensional geometry. So thank you very much for your attention.
Thank you. Any question?
I wanted to ask, is this chip safe against possible noise sources, or I don't know? I mean,
so the advantage of this chip technology, you may have today I described the U1 chip technology, which is laser writing. So you have plenty other technology, silicon technology, silicon nitride. The advantage of being on chip is that you are not sensible to vibration because everything is monolithic. So this interferometer, when we fabricate them, they stay forever. Then depending on which kind of parameters you want to have on the chip, for instance, now we are working on some chip which are reconfigurable. This means that you have your chip, you have some timing control on it, and you would like to change which kind of evolution you implement on the chip. So you have the chip, you have some thermal resistor on the top, and by changing some knobs, you can change what kind of dynamics you are investigating. In that case, since you are eating your device, you must be more careful. But in general, this technology is very stable against any other kind of interaction from outside.
okay, so you are pretty sure that the evolution is unitary?
Yeah, so if you are concerned with the coherence, it is very low. What you can have, our main limitation today are losses. So losses are not negligible. This means technically we are working on post-selection. Other technological platforms have much better losses.
Thank you.
Other question?
Oh, hi. Let's consider a case in which we have in the boson sampling some cutted wave lines and waveguides. And where does it happen? I mean, is there any study about quantum calculation threshold? You understand the question?
So your question is more, so that's another side of boson sampling. So today we focused on boson sampling because my goal was to show you this platform can beat in 3-5 years any classical computer. But you can also see boson sampling as a quantum walk. So because basically you are mapping the dynamics in your optical networks. So if you see boson sampling as a quantum walk, then you can engineer your structure, and depending on how you engineer your structure, you can see different features. For instance, you can have graph, you can imagine that this is a quantum walk that you can describe with a graph. If you cut some line, you are right, you have a graph where you can investigate some percolation. So some theoretical works have been done. I don't think yet an experiment. If you want to investigate these dynamics, you will need, I can guess, some long chip, because you would like to have many steps of quantum walk. But that's something which is, you have many theoretical papers on quantum walk dynamics. Experimentally, this dynamics has not been yet investigated.
So this system to work, we need to have a photon synchronized, no?
Can you speak a bit
to
louder?
Synchronize the photon, you use the delay lines.
Yes.
But there will be always some uncertainty, no?
Yeah, but you have to imagine that you want to, what is the physical parameter of interest is the coherence time of your photons. So our photons have a coherence length of 200 femtoseconds. So this means that the wave packet of each single photon is something like 50 microns. You can have a delay line with a precision of 1 micron, which means that the overlap of the Gaussian beam of the wave packet will be something like 99.9. We are not perfect, but quite close. You have other technology like quantum dot single photon sources which generate much longer wave packet, where the length of the wave packet is 30 centimeters. So if you synchronize something which has a length of 30 centimeters with a precision of 10 micron, the overlap of the wave packet will be 99.99999. So that's not, you can control how much is the imperfection and keep it below some threshold.
Other questions?
Maybe it's a stupid question, but I didn't get if from one chip you can have just how can I say, just a word. I mean, the sequence of one. So in order to have more words, you have to build a specific chip, right?
Yes.
Okay.
So you're right. Each chip, up to now, what I've shown you, each chip is a different unitary evolution. So each time you want a unitary evolution, up to now you have fabricated a new chip. During the fabrication, you decide the parameter. But now we are introducing the reconfigurability. So you can have a single chip where you can have some control on the chip. Recently, MIT, they had a chip, a nanophotonic chip, where they could change 50 parameters. Now we are at 5 parameters in Roma, Milano. So you have a chip where you can still change. You cannot change everything, but you can change some parameter of your unitary evolution.
How?
What you do is that you have a device where you have that's a chip, you have some thermal contact on the chip, you are heating the chip very locally. By heating the chip, you are slightly changing the index of refraction. This means that you are changing the optical path. This means that you are changing the phase, is acquiring the optical beams. Obviously, this is a very small thermal contact, only very small, because you would like to change something which corresponds to a phase shift, which is a very small change.
Thank you.
Yeah, also concerning the reprogrammability of the chip. So these methods of reprogramming the chip are using thermal methods, which means they are pretty slow, I guess.
Yes.
Are there any perspective to use maybe faster methods, such as like an electro-optic modulator or something?
Yeah, so before I told you about thermal contact, where you can change the unitary transformation, but this will require seconds, because you need to thermalize the effect. This is not usually a problem for this kind of application, because the experiment still takes hours. So if you lose 10 seconds to change the unitary, it's not a problem. But if you want to have faster application, you need to have other devices which have, for instance, electro-optic effect. That's the case of lithium niobate. So you can have some integrated technology over different material, and this material have electro-optic effect which allows you to change it on a very fast time scale. This is adopted for classical technology at telecom wavelength, where you have some integrated chips that are used to multiplex information over fiber networks, and they use this kind of effect. What is the problem of moving this in the quantum domain is that usually this technology have today a quite high loss. So when you go in the single photon domain, you pay a price in terms of brightness of your experiment.
Okay, thanks.
Okay, other questions? Okay, we can thank Fabio again. Okay, now there is the coffee break upstairs, but before I have two information. The first is that due to the initial delay, the next session will start with 20 minutes delay, so we start at 11:50. And the second information is that if you are interested in the visit to the observatory, you have to confirm at the desk during this coffee break. Thank you.
quanto vuoi, io il tempo che ho, nessun problema, non ci metteremo assolutamente. No, vabbè, grazie di essere qui.
Grazie per essere venuta.
Funziona. Alessia è presente in sala? Ciao, ci dovresti dare la presentazione. Credo tu ce l'abbia data, ma magari non ricordo. È quella lì. Ah, ecco. No? Eccola, ok. Quindi metto 2, scusami, perché generalmente io le metto in funzione del... No, soprattutto metto prima il nome. E lui dovrebbe essere... Però dovrebbe essere il terzo per me. Allora, vuoi che te la apra, giusto? Così la controlli, verifichi. Certo. Scusami. Ecco, sì, no, è il... Perfetto. Grazie a te. Il controllo L non ha funzionato, coppa. Nel video su YouTube a fianco appare la presentazione, quindi tu non la copi. Tecnicamente potresti muoverti avanti e indietro, però se sei fermo in funzione della telecamera, questo per te. Poi hai tu durante. Perché trasmessa
Prova voce, prova. Good morning, my name is Alessia, and I'm going to speak about the ice formation, about the formation of ice crystals where in clouds. And the main actor of my presentation are specific aerosol particle able to trigger the formation of ice crystals. So, because the main actor of my presentation are aerosol particles, just to speak a little bit about aerosol, why they are so important, where they come from. Aerosol means solid or liquid particles suspended in air, and the size range go from few nanometer up to about 100 micron, and so on. So, good morning, everybody. My name is Alessia, and my presentation is going to lift you up to the troposphere. And just to let you understand better the title of my presentation, I'm going to speak about. Vediamo se si sente meglio così. Good morning, everybody. My name is Alessia, and I'm going to take you up into the troposphere. The subject of my presentation is the formation of ice crystals in the troposphere. In the troposphere.
dice Alessandro, stavo andando, io parto, So now we can start with the geophysics section. The speaker is Alessandro Ursi from INRiM, Rome. He speaks about detection of terrestrial gamma ray flashes by the Agile satellite. Thank you.
So good morning, everyone. I'm going to talk about the detection of terrestrial gamma ray flashes with the Agile satellite. So I work with the INAF, Institute for Astrophysics, and also we are performing a study with the Climatology Institute in Rome. So maybe some of you is wondering what a terrestrial gamma ray flash is. So before starting, just a few words here. This is our atmosphere, different layers with different temperatures and densities. And of course, we know that in the atmosphere we have clouds, okay? So clouds made of water vapor mostly, and mostly concentrated in the troposphere region. So among the different type of clouds, we have a special kind of clouds, which is the cumulonimbus cloud. It's a very tall environment here. You can see up to 9, 10, or also 12 kilometers altitude in some latitudes. So this is important because by a very complex mechanism involving ice at the top, which is very cold, and hot water at the bottom in a liquid form, a charge separation can be induced. So cumulonimbus clouds are mostly known as thunderclouds. Okay, thunderclouds have an electric field inside. An electric field could also be established between cloud and ground by induction, or between a cloud and another cloud. So of course, when you have an electric field, you should discharge it. So you have different ways to do this. The most common way is lightning discharge. We all know lightning. These are sparks lasting fractions of seconds and with an average length of about a few kilometers. You can have intra-cloud lightning within the same cloud, cloud to cloud between different clouds, or cloud to ground, as I said before. They have pretty huge voltages here. I'm talking megavolts here. So of course, we all know lightning here. Some images from the International Space Station. Different paths, very randomly distributed here to see the... And also we observed lightning on other planets like Jupiter, for instance. But maybe you don't know that in the last 30 years, a whole new family of discharges, of the phenomena have been discovered involving new kind of discharges occurring over thunderstorms. So these are mostly referred as transient luminous events. Here they have a strong impact on the ozone production, and they also interact with the ionosphere and magnetosphere system. And they're mostly discharges, upward directed discharges, that interact with the chemical components in the atmosphere and produce these optical glows, reddish, bluish. So here's some pictures from the International Space Station over a thunderstorm here, a red sprite, other red sprites here. This is a blue jet, a sort of upward lining. Red sprites, another discharge here, gigantic jet. And among them, we have also another kind of phenomena, which is terrestrial gamma ray flashes, and these are gamma rays escaping to the sky. So this is mostly how a terrestrial gamma ray flash looks like. Of course, these are gamma rays, so you cannot take a picture of that. You have to deal with detectors aimed at detecting gamma rays. So you have to count the number of photons and the released energy in the unit time. So this is the typical light curve of a TGF. It's not as much as picturesque as this phenomenon here, but it's pretty interesting. So what are just a few words about the discovery, because it's a serendipitous discovery, as often occurs in physics. So we know that in the 60s, there was, after the Cold War, US and Russia, there was a sort of nuclear test ban treaty, in order to forbid nuclear tests on the Earth. And the US delivered into orbit these Vela satellites, which were aimed at detecting gamma ray signatures from nuclear tests on the Earth, But what they detect actually were gamma rays coming from the sky, a phenomenon that was later termed gamma ray bursts, So gamma ray bursts are the most powerful explosions occurring in the universe. So it drove the attention of the scientific community very soon. And in 1991, it was the first mission, the Compton Gamma Ray Observatory here, CZRO, which was the first mission endowed with detectors aimed at studying these gamma rays coming from the sky. But what they did detect were actually gamma rays coming from the Earth. And this phenomenon was later termed terrestrial gamma ray flash. So this is a terrestrial gamma ray flash. It's a huge amount of photons released in a very narrow time interval. an average duration of about 100 microseconds. So it's shorter than the shortest gamma ray burst you can measure. And as you can see here from the spectrum, so the energy distribution, it's a rather hard spectrum. And from simulations, we can infer that the altitude is about, the production altitude is about 15, 20 kilometers above sea level, mostly 15. These are associated to lining. Why that? We have two strong conformations. The first one is, if you take a look to the lining distribution on the Earth, you see that lining mostly cluster over the land here and over the continents, and they cluster in the tropical region where most of the intense thunderstorms take place. And you see here, these are all TGFs detected up to now, and you see that this distribution is pretty the same. Moreover, here that's impressive, this is a meteorological feature of the Congo Basin, and here you have a sharp cut in the lining distribution, and this sharp cut is also followed by the TGF population here. So you see that there is a correlation between the two phenomena. And another confirmation comes from spheric. Spheric waves are radio waves emitted by lining. We know that a significant fraction of lining energy is released in the radio wave about VLF here. And these radio waves propagate within the Earth ionosphere system, can be detected very far away. And whenever we detect a spheric, we detect a TGF from upside, well, with a satellite, we can go and look whether a radio network has observed something coming from the same region. So we observed many of these correlations. So it means this is a pretty difficult measurement to perform because it requires a very good time accuracy. But there are many matches between TGFs and lightning. So just a word about the production mechanism, because these are the most energetic, this is the most energetic phenomenon occurring on the Earth. And this is Charles Wilson, the inventor of the cloud chamber, and in the 20s, he suggested the thundercloud behaves as the most powerful particle accelerator, natural particle accelerator on the Earth. This is true because we have megavolts as potential here, and if you have a seed, like a charged particle, a cosmic ray, or an electron outside the thermal distribution here, it can act as a seed, it can be accelerated, it can ionize an atom and molecules here inside, can rip electrons out of these atoms, and produce other secondary electrons, and these electrons are also accelerated, giving rise to an avalanche process here. This avalanche process is called the relativistic runaway electron avalanche, and when this avalanche, we're talking multiplication factor of about 10 to the 17, 10 to the 18, so it's a rather huge number of particles. When they reach the top of the cloud, they are abruptly braked into the atmosphere, and they produce gamma rays via Bremsstrahlung process. So this is interesting. This is hazardous because we are dealing with gamma rays, extremely energetic gamma rays, occurring at airline altitudes here. So this is a cumulonimbus cloud with a typical anvil shape, and this is an airplane wing. And we know that also every aircraft is struck by a lightning stroke once per year. So now the aircraft is mostly a conductor, so it's not a problem this. But if here there is a huge emission of gamma rays, this could be dangerous, both from a biological point of view for the crew, but also for the electronics on board. And so this is interesting in the sense that the TGF rate, so the radiation dose emitted by a TGF in less than 1 millisecond, is something like 10 to the 12 times the total amount of radiation we are exposed to in 1 year from the environment. So it's pretty huge. So we have to take attention about that because that's not so. Okay, as I said before, over thunderstorms, we have to detect these phenomena, and because they are directed to the space, and of course the thunderstorm absorbs the radiation in the gamma rays. So up to now, most of the detections have been carried out by high-energy astrophysics missions like the Compton Gamma Observatory, BAPUSAX, RESI, the Agile satellite, and also the Fermi Space Telescope. So I work now on the Agile satellite. The Agile satellite is this guy here, is this small box here, or the spacecraft. And we have a mini calorimeter, which is mostly an all-sky detector with no imaging capabilities, so it's mostly a segmented scintillation detector. You have gamma rays, and you can detect gamma rays coming from wherever. We have a silicon tracker with imaging capabilities. It exploits pair production, so it means that when a gamma ray or particle crosses the detector, it produces a positron-electron pair, and by measuring the time delay and the energy released by these particles, we can infer and reconstruct the incoming direction of the photon. Then we have a coded mask here, and of course an anti-coincidence model all around made of plastic scintillation detectors. Okay, in Bruno Rossi, in 2012, it was awarded the Bruno Rossi Prize for the discovery of the variation of the Crab Nebula. So if there's some high-energy astrophysicist here, knows that the Crab Nebula is a very stable source, was thought to be a very stable source in the gamma rays, but it's not. So something about our detections with Agile. So we performed the first imaging of a TGF. So we performed the first imaging of something, of gamma rays coming from the Earth. So this is our detection in 2010. And we see here that, of course, the cluster of the continents. And this is the most common 6-degree uncertainty radius around the footprint. And we see that the red dots are photons. So we were able, or we are still able, of detecting photons and to reconstruct the incoming direction of these photons. So this is the first time a gamma ray detector is pointed towards the Earth to observe what's happening. Another interesting thing is that the former instrument was RESI, and RESI has an energy range up to 20 MeV, but we have an energy range up to 100 MeV. So this was RESI observed. This is the spectrum with a sharp cutoff here, but what we observe is something with a rather harder tail. So it means that there is another population, maybe, or there is something else that leads to the production of very high energetic photons here, up to 100 MeV. So that's pretty a huge work. We are working very hard on this now, so stay tuned because we are trying to make an assessment of this high energy spectral component now. Okay, we published the first catalog here. There were just 308 TGFs. Now we have more than 1,000. And okay, last year we know that TGFs, they are very small, very short duration events, as I said before, so 100 microseconds. So it means that every detector detecting TGFs has to deal with dead time, okay? And our anti-coincidence modulus, which was the shield all around, induced a sort of 5 microseconds dead time. So we switched it off, and our detection rate rose up from 7 TGFs per month up to 70 TGFs per month. So our detection rate now is the highest among the TGF detecting satellites. And of course, this prevented us from observing the shortest duration events. So now this is the new TGF distribution, peaking at about 100 microseconds time duration. This is the T9A. And these are two works. Maybe I just spend a few words more. Of course, TGFs have been detected by high-energy astrophysics missions up to now, but they are completely terrestrial phenomena. So we have to deal with meteorology in this case and to understand what's happening in the lightning process, what's happening in the thunderstorms. So for the first time, we linked TGFs detected by a high-energy astrophysics mission to information from meteorological satellites. Of course, you can have two kinds of meteorological satellites. We have geostationary satellites, which are continuously observed in the same region on the Earth, and low LEO satellites, okay, which are orbiting around the Earth. So now the basic idea is to go and see as fast as possible to the region where Agile detected a TGF, what's happening from a meteorological point of view. And so the probability to have both Agile and a LEO satellite flying over the same region at the same time is pretty low. So we just use these geostationary satellites for the moment. This is the global coverage of geostationary satellites. Of course, there are many other geostationary satellites, but these are the ones we use for our pipeline system. There is the US GOES satellites, the European Meteosat 10, the Chinese Fengyan 2, and the Japanese Himawari 7 and now 8. And all these data are continuously downloaded at the Climatology Institute in Rome here into a 1-week buffer memory. So this is the basic principle. We have thunderstorm here producing a TGF detected by Agile orbits down to Malindi in Kenya, and in the ground station it telemeters data to Rome, to our system. And then also we select the most suitable instrument, the most suitable geostationary satellite here that would have been observed in the region where the TGF is coming from. And this geostationary satellite, of course, sends these data to the ISA Climatology Institute. So whenever we detect a TGF, we produce a sort of ID card here with the position, the light curve, the number of photons, the energy involved, the position. And we also select this satellite. In this case, this is the Meteosat 10. We can reconstruct some meteorological information here into this uncertainty circle around the subsatellite point. So for instance, we can reconstruct the cloud top temperature. Cloud top temperature, of course, is it's good at identifying also convection, because convection, as I said before, is linked to thunderstorm system, to cumulonimbus clouds, so very tall environments. And tall environments means also low temperatures. And the same also cloud top height. So here you see that you're linked to a very complex mechanism here involving very high clouds. Of course, you can have some false results, like cirrus clouds. Cirrus clouds are ice clouds, very, very high clouds, but not linked with convection. So we can also use some algorithms aimed at detecting, at identifying convection, at highlighting convection. So in this case, cirrus clouds don't trigger this algorithm here. And so these are the most convective regions in this circle. Of course, we can also plot from lightning location network station the lightning spherics here, so the lightning strokes occurring. And okay, what else? LEO satellites, microwave sensors, presence of ice, CAPE. We can do many other things. Okay. What else? Okay, we are open, so if you have ideas. Last thing here is a peculiar characteristic of the edgeless satellite in this field. So here we have a very, realistic thunderstorm here. If we take RASI has a 38 degrees inclination orbit. So it means that if it crosses a thunderstorm here, at the second passage it won't cross this thunderstorm. It will experience something like a 15 degrees inclination shift, a latitudinal shift. At this, in the tropics, it means 16, 17,000 kilometers away. So it's very far away, so it cannot see the same thunderstorm. Same thing, more or less, for Fermi, which is 26 degrees inclination orbit. It would experience something like a 10 degrees shift. But Agile has the lowest inclination orbit ever achieved by a high-energy astrophysics mission. So in this case, we have a 2.5 degrees inclination orbit. We would experience, in the worst case, just 1 degree latitudinal shift. So we have a flat orbit. We are continuously observing the same region. So we can perform a sort of follow-up of these thunderstorms. This is the waiting time distribution between successively detected TGFs. And as you see, this is not a simple Poisson decay, as expected from non-correlated events, but there are some bumps here, which corresponds to the first, the second, the third, the fourth, and so on, resonances. Okay? And by studying these correlations here, we ended up with 79 systems capable of producing more than 1 TGF, either during the same passage, or at the first, the second, the third, and so on, orbital resonances. So in some cases here, here we detected during the same passage 2 TGFs coming from here. Here another case, 2 TGFs coming from here from the same thunderstorm. Here 3 TGFs during the same passage, and here 2 and 2, all during the same passage. What about multiple passages? Here we are observing something at 5:50 in the morning, and 5:15, sorry. And now we perform a whole revolution around the Earth, and we pass again here, and we detect another TGF coming from the same region. And then after another orbital resonance, we detect another TGF. And then other 2 TGFs at the other passage. So, and here, again, another case. We detect a TGF here, and after 2 passages, another TGF here. This is also interesting because we have, as I said before, we are not using LEO satellites because the probability to have a LEO satellite fly over the same region is low. But in this case, we were lucky. So there was the Global Precipitation Measurement Mission. And this is not a geostationary satellite, so its orbit is at about 500 kilometers altitude, not at 36,000 kilometers away. So it has different instruments, like radar measurements, so it allowed also to perform a reconstruction, a longitudinal reconstruction here, the vertical profile, the content of ice, and we see that we are dealing with a very high overshooting top here, a very high thundercloud. So, just ending, okay, I hope you discovered a new kind of phenomena, maybe these TGFs, which are the most energetic natural phenomena occurring on the Earth, and we have to pay attention to them, okay, to study them better, because they could be hazardous for aircraft. And from the point of view of Agile, we have the highest TGF detection rate to date. We have the possibility of detecting multiple TGFs from the same regions. And we are also having now an accessible meteorological pipeline at the Climatology Institute. And of course, all this stuff could help in shedding light on these open points, like all thunderstorms produce TGFs. There are some specific kind of thunderstorms or not. How common are TGFs? Every lining discharge has an accessible TGF, okay? And other constraints on the production mechanism, like, okay, the TGF triggers the lining discharges, the lining discharge that triggers the TGF. So we don't know that. So this is a very brand new field of science, and thank you for your attention. So.
Are there any questions?
I would like to know if, based on how much time the satellite is pointing to the storms and so on, you have any better clue on how this phenomena is common in storms, and in general how did you expect the distribution of these events going on?
I believe